Okay, as you can see, it's got the text there so we can see what our text looks like. All right, here's what we're going to cover today in this class, at least this first section. We're going to take and determine what a function is and how to look at it in its different formats. A function, and let me define it for you first, but I'm going to show you the different ways you can see a function. Now, here's what I do want to tell you guys. I like it if you guys talk back to me, because it's no fun if I just sit up here and talk and y'all just listen like, okay, we don't really want to hear what you got to say. But I like it if you guys talk back to me while we're actually having this math class. So I want to start off by going over what is a function. This slide is just telling me what we're going to cover today. So we're going to determine what a function is and the different types. We're going to talk about what a domain and range are, a scatter plot, which is when you put it in a graphing tool, the function notation, and of course, this is a word problem class. Y'all did know that, right? Okay, this is a word problem class that we're going to have fun with because you want to see how it relates to real life. That's the question that we get all the time. How in the world does this relate to real life? Well, that's what we get to do here. So here is what the definition of a function is. It says that it's a rule or correspondence that assigns to each element of one set and exactly one element of another set. Does that mean anything to you? No. You're like, okay, so you gave me the definition. How does that make sense to me? Well, let me show you a different way to look at this. Do you guys have a washer dryer at your house?
Yes.
Do you know somebody that's got a washer dryer? If you don't have one at your house, do you know somebody that has one? Okay, so I'm going to have to use this board because I can't reach that one that's up high. So here is my dryer. Okay? Does something go inside the dryer? What? Just any kind of clothes? What kind of clothes? Wet clothes. I do know people put dry clothes in there to get the wrinkles out, but its main purpose is what? Dry the wet clothes. So right here, we're going to have wet clothes on this side that go inside the dryer. What comes out? Dry clothes. Okay. Okay, so what we're trying to say here is I'm trying to give you a very simplistic way of understanding what a function is. It said that there's something that happens inside this dryer. Do you care what happens inside the dryer? No, as long as it dries your clothes, you don't really care. Well, in this case, something happens inside of here to cause the clothes to become dry. You put something in, you have a set of clothes that go in. Do you get a set of clothes out? Yes. If you put a wet red shirt, do you get a dry red shirt out? Yes, you do. So if I take one set, do I get another set out that have been changed?
Yes.
Yes, I do. They have now been changed to dry clothes. Well, can we see this as a set of clothes? And this is a set of clothes. There's still something happened to them and they came out dry. That's a function. This is just a very simplistic way of understanding one set of something, one set of items, something happens to them and it produces another set. In that description, it says a function is a rule or correspondence that assigns each element of one set to exactly one element of a different set. If I get a red shirt, do I get a red shirt over here? Okay. If I put a red shirt in here, do I get a blue shirt over here? So it's got to be exactly one item matched to one other item. Does that make sense? All right, so let's use it and let's take it a step further. What if I decide I want to plug in number 2 and I want to get out a number 10? What has to happen inside this dryer in order for 2 to become 10? I can do what? Add what? 8, or what else can I do with other than add 8? Multiply by 5. Subtract what? Okay, so you're looking at different things that I could do. So I'm going to say I'm going to multiply by 5. So here inside the dryer, we're multiplying by 5. Here's what happens inside of here, and we get a 10 out. One thing goes in, and what? One thing comes out. That's what that definition says. Now, we've got different ways that we can see what a function looks like. So here are the methods of what you can see that one looks like. We're going to look at it as a set of ordered pairs, a table, which means an XY table. Now I'm looking at paragraph number 2 here. We're going to look at it as a set of ordered pairs, a graphing XY table, a graph, an equation, and then a verbal description. These are the different types of functions we're going to describe now. All right, the first one says ordered pair. I'm writing a set of ordered pairs up here on the board. These are called ordered pairs. I got 1, 10, 2, 20, 3, 34, 40. This one is called my X, and this is called my what? Y. Usually in the homework it'll call it the X coordinate, same thing as X. And over here it's called the Y coordinate. It's just a mathematical name. Okay, so you got your X and your Y, each one of them. Can you see how I, again, plugged in a 1, which is my X value, and I ended up with a 10. I plugged in a what? And got a, plugged in a 3, I plugged in a 4. What's happening inside the dryer so that this happens as my answer that comes out? Multiply everything by 10, and those are the answers I get. Okay? This is called the what again? What are these called? X and Y coordinates for a set of ordered pairs. Is this a function? Yes. One number goes in, you get one number out. If I put in a 2, is it possible for me to get 50? With this set of ordered pairs, could I plug in a 2? What's the rule? When we say what's the rule, I want to know what happened inside the dryer. What did we do to get these numbers? Okay, so here's the rule that's happening inside the dryer. You multiply by 10, that's what's happening inside. Can I plug in a 2 and get a 50? No, you can't. Okay, that totally defies the rule here. So we can't do that. All right, so you got the table, the XY table. What's the next one? I mean, not the table, but the order pairs. Here is the next one that we're going to do. I'm going to do an actual XY table, and I'm going to use the same numbers that I already have on the board. I'm actually looking for a tissue since I don't have an eraser. I was trying to see if they had one in here somewhere else. All right, I'm going to have to use my hand, guys. All right, here we go. What's the difference between this one and this one? Between this one and...
It's actually on the X and Y coordinate.
It's just the XY table. There's no difference other than these are called what again? And this is called what again? That's the XY table. Same information. Is it still a function? Yes, it is. In the homework, it's going to ask you, is y a function of x? When they're asking you, is it a function? That's why I usually say, is it a function? In the homework, they're going to say, is y a function? A function of x. So these two statements mean the same thing. I'm asking you the same question. Is it a function? I'm asking you, is this a function? Is this a function? Your answer was yes. And the homework is going to say, is y a function of x? It wants to know, does y get produced by x? Does something happen that y gets produced by x? Does something happen to x to produce a y? Yes. That's what they're asking you. Does something happen to this 2 to produce 20? Yes. So does y get produced by x by associating or relating to x? Yes. I'm just saying in the homework, they're going to ask it this way. Now, here's the question I have for you. Do you always have to use x and y? No. No. Could I make this C and D? Yes. F and G? Q and R? Don't assume that they're always going to use x and y. Do not assume that. So what if I change this, because I need for you to see it a different way. So what if I change this and I made this C, I made this D, and I did 1, 3. Alrighty? Now, how would I rewrite this question to refer to the letters, the variables that I've just given you? So in the homework, here's what it's gonna ask you is, I know this part is gonna stay the same. Now, is it gonna say, is C a function of D, or is it gonna say, is D a function of C? So I should put a what here? Thank you. So just notice when they ask you the question, looking at this statement, the Y is coming first, they're asking you that question. Over here, the D, so it's the output. So just remember, when they ask you the function, this variable should always be the output. And this variable right here is always going to be the input. Okay, so let's talk about input and output because we didn't say that. What goes into the dryer is always called the input, or we could also call it the X, or whatever letter of the variable they want us to call it. Over here, thank you. Over here, what's coming out is called the output. There we go. And in this case, we've been calling it the Y. So whenever you see the question being asked here, whatever the output variable is what always goes here. Whatever the output variable. Do they have to put the variables in the right order? Like I put C and D. Do they have to do C and D in order? No, they could have switched it and put D and C. So just make sure whatever the output variable is always what goes here if they rephrase the question. All right, you okay? Okay, so we just did the ordered pairs, the XY table, and here's the graph. So here's the next one. Here's the next one. It is the actual graph. And so here is a graph of a straight line, uphill line. They want to know, is this a function? So they're going to just give you a graph and say, is that graph a function? It has to pass the vertical line test. The blue line that you see must pass the vertical line test. Okay? I'm going to draw one line. One vertical line has to be up, straight up and down, not leaning to the side. I'm going to draw just one. Did it touch the blue line? How many times? Once, then it is a function. How many times can it touch it? Just once. Can only touch the blue line one time. You can only draw one vertical line. Doesn't matter where you draw it, as long as you can see if it touches. So, does it pass the vertical line test? Yes. So this one is a function. Look at this graph here. Here's a different graph. Let me label my X and Y axis. Do you guys remember this is your X axis? And this one was your Y axis? All right, here's a different graph. Is it a function? So if I draw one vertical line, it touches that curve how many times? Twice. Not a function. The next one is an equation. So if I give you an equation, and here's the equation, x squared plus 2. That's just one I just made up. That's the equation. I want to know if that equation is a function. Well, you've got two ways you can do it. You can come over here and plug some numbers in and create an XY table. Or you can just put it in the graphing tool and see what the picture is going to look like. So you go straight to Desmos or your graphing tool that you're using, and anytime it has x raised to the 2 power, it's going to look like a U shape, which we call a parabola. So this is what that's going to look like. So I would go type it in the graphing tool and see what the shape looks like. Does it pass the vertical? And then see if it passes the vertical line test. Does it? Look at it. I'm gonna draw. Okay, so here's my. Y'all looking at my. I don't have my x-axis. Here's my x-axis. Here's my y-axis. That's the curve. Do I have to draw one vertical line? Does it pass?
Yes.
Passes. So is this a function? Yes, it is. Yes.
Can I have a question?
Yes.
What if the line is like way on the end of the U where it technically, you know what I mean? Like, am I overthinking it?
Like right there.
Yeah.
It's still gonna touch it only once.
Mm.
So here's what I hear you saying. You're saying, I'm trying to draw it better. You're saying, what if that U looks like it's too straight up and down? So if you draw one vertical line and look like it touches too much, you'll be able to see clearly that it's gonna touch it properly.
Okay.
So they're not gonna give it to you, so you have to wonder. So if you got one like that, well, you can see clearly that one's gonna pass. So you'll be able to define it easily. It won't be so difficult that you gotta like, wait, I can't tell if it does or doesn't. Alrighty. So that was the equation. The last one is called the verbal statement. Is it a function or is it not? Alright, so here's an example. Your cell phone bill in any given month. Cell phone bill. Okay, your cell phone bill in any given month X. You're like, how in the world are we going to use this? Well, guess what? You have to go create an XY table. Well, it tells me what X is. Usually whatever X is sitting next to is what X is. So X happens to be my what? Okay. So X is my months of the year. What are they? Of course, you know what they are, right? January, February, March, April, May. All right, so they're my months. All righty, so the question becomes, now that we've got the months out there, what's my Y? The other conversation piece. What are we talking about? What are we talking about? Your cell phone bill. So one of these got to be the X and one got to be the Y. Well, they will always tell you what the X is because they'll say month X or day X or whatever it is they're going to say. They'll tell you what the X is, but you have to figure out what the other part of the conversation is that tells you what the Y value is. So what might your cell phone be? That's your Y. This is the bill, cell bill. Alrighty? So, in January, your bill might be $100?
141.
141? Okay, let's get it. Let's be specific. Let's be specific. 141. Now, does your bill change? Depends. If you go use your overage, you go over it, then it does. And if it doesn't, it stays pretty much the same, right? Okay, so we can say it was the same, it was the same, it was the same. Then we had some overage fees and some overage fees. Then it went back to being the same all the way down to the end of the year. All right, so question, is this a function? Now, if I had to graph this, it would look like, again, I could put this in a graphing tool because this is month 1 for January, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I would have the numbers 1 through 12 here if I wanted to graph it, and I would put these in here as the numbers. Would I have something that looks like something that would pass the vertical line test? And so here's my question to you. Why does this one pass? Why that one can't pass? Why does this one right here pass? Why that one can't pass?
Because of the simple fact, like,
If I plug in January, do I get a bill statement in the mail? Think about it now. If I look at my January, does Verizon or Sprint or T-Mobile send me a bill in January? Yeah, okay, well February, do they send you one in February? If I plug in March, do I get and if I plug in April, do I get a bill? So again, in most of what we'll do in this class, it'll be mathematical. This one's not mathematical. It's just saying if you plug in a month, what happens inside the dryer? The bill company produces the bill for you and sends it to you in the mail. So what comes out? You get a bill. Right? So can I call that a function? If I plug something in, do I get something out? Does it matter that my bill is the same every month? No. Is the value the same every month? That's fine. I don't have any problem with the fact that my bill stays the same every month. So as long as you plug one thing in and you get one thing out, that's fine. Here's where it's not a function. If you're like, well, when is it not a function? What if up here I had January twice? Did you get 2 bills in January? I don't want to pay the one I got. I definitely don't want to. So the question is, no longer is it a function if you have 2 Januaries or 3 Januaries or 4 Januaries, or you can do any month, 4 Februaries. If you have duplicate X values, it's no longer a function. All the X values have to be different. So you have to create a table and make sure all X values are what? Different. If all the X values are different, it's a function. All right, questions? Let me log back in. Alrighty, so we've covered a couple of things while doing this, so I'm gonna go through the slides here so I can see. All right, did we do the order pairs? Did we do the XY table? Did we do the graph? Equation? And a verbal statement. All right, you've got all the different types of how we can represent a function. You can represent it this way, this way, this way, all the different ways they can show you that function on the homework. And they want to know, is it a function? So let me make sure we're clear. If all the X values are different, is it a function? Yes. If all the X values here are different, is it a function? Yes. Here we have to pass the vertical line test to see if it's a function for both the graph and the equation. With the verbal statements, you have to create an XY table and see if all the X values can all be different. Okay? We're okay? All right, next slide. All right, everything in this class relates back to real life, and so we want to use this to kind of pull in some information. All righty, and I didn't want to do this slide here, but we'll go ahead and put it in. Suppose a child's normal temperature is 98.6 degrees Fahrenheit, but the thermometer that you have is a Celsius thermometer, and it indicates that the child's temperature is 37 degrees Celsius. Does this reading indicate that the child's temperature is normal or not? So the question is, how would you know? If you had a thermometer and it was only a Celsius thermometer, how would you figure out if your baby had a temperature or not? You would plug it into this formula. So they're saying that there's a formula that we can use to plug in to see what the actual Fahrenheit temperature. Because if you were in a different country, a lot of countries don't use Fahrenheit, they use Celsius. In the United States, we use Fahrenheit for our temperature, right? But what if you weren't here? What if you were in a different country? Would you know how to change it? How to convert it? This is your formula for converting from Celsius to the Fahrenheit temperature. So, did that child have a temperature if the degrees said 37 degrees Celsius? Look what happened. In the place of the Celsius temperature, everywhere there was a C, we put a 37. And we did the math. You literally can put this in your calculator. Why did I get the, say it again? Why did I get the 9/5? This number right here, the 9/5, is part of the formula. So literally there is a formula that if you plug in 37, it'll tell you what the actual American Fahrenheit temperature is. So this is what was already created for us. That was already there. So C represents the temperature in Celsius. which was 37 degrees, and I want to know if my child's temperature is 37 degrees, do they have a fever or not? So if I plug in 37, do the math on your calculator, I get a Fahrenheit temperature of what? 98.6. Does your child have a fever? No. That's pretty normal. So now, if I keep plugging in numbers, will I get a number out? If I keep plugging in numbers, will I end up with an XY table? Can I create an XY table from that? But in this case, what letters of the alphabet are we using? We ain't using X and Y. What are we using? Alrighty. So, what's input for this one? What's input? C. So Celsius is going in. What's coming out? Fahrenheit's coming out. Okay? All right, so that's C and F. All right, so if I plugged in 37 degrees, what do I get out? 98.6. If I go plug in a different number, if I plug in 54 degrees, what do I get out? Somebody tell me what that is on the calculator. Plug in 54 degrees, what's my baby's temperature? So you're plugging into that formula that you see on the screen. Y'all not going to take a chance and see what you got?
129.2.
Not gonna let my baby's temperature get to be that high, you know. So again, you see, if you plug one number in, do you get another number out? Yes, it's a formula, but you're still using it as a function. Plug a number in, get a number out. Plug another number in, get another number out. This is just telling me if I plug in Celsius, I'm gonna get a Fahrenheit temperature out. Questions? All right, next slide, here we go. For each of the following graphs of the functions, find the domain and range. All right, so they've given you points already on a graph. They just want to know, can you name these points and put them in an XY table? Okay, so this point right here, did they name this one? What is that point based upon what you see? Let me see, see if I make it bigger. All right, based upon what you see, what would you name that point as an ordered pair? What would you name it? Or on the XY table, this point right here, what would you name it? -5, -7. I agree with you. Is it on the table? Yep. What's the next blue point up that you see? The next one right above my finger. -3, -2. That's next. Next point.
0.
0, -2. All right, next one. Wait, I missed one. What's the one way up at the top by the 6? -1, 6, then the 0, -2. What's this one next? Right here, above my finger. 3, 5, and the last one. Okay, so all they did was ask you, what are these points that's on this graph? Can you name them and put them into an XY table? In the homework, it'll say create a scatter plot. So it wants you to take this information that's in the XY table and put it over here so the dots pop up on the screen. So you literally, all you do is go to Desmos and start typing in points. So let me go to Desmos real quick and just show you that so you know how to do that. All right, here's Desmos, so let's delete this. See this plus sign up here at the top? If you click on it, it gives you a choice of doing some things. We're gonna click on table. And now I can literally start typing things. 1, 10, 4, 5, doesn't matter what we put in here. We just put numbers in. 2, 5, 3, 7.
How did you get the X and the Y like that?
It immediately does it once you start typing numbers. So let's delete it and start over again so you can see. Hit the plus sign, click on the table, and it automatically puts your X and Y's in there just like that. And you just type numbers 1, 2, 2, 4, 3, and I'm just using my cursor to come down to the next box, 5, and you can see your dots just pop up over here. And this one, -3. So when it says create a scatter plot, This is all you have to do. Type it into a table in the graphing tool. Questions?
Are we supposed to make an account and you can go on there and see it?
No. You don't have to download anything to do anything with this one. Literally, and let me close the window and open it back up again. Let's Google. Yes, leave. So here, if I go right back to desmos.com, this is the window that pops up. You don't have to download anything. Click Start Graphing. That's it. You don't have to create an account or anything. Questions? All right, back to the PowerPoint. All right, so you see how we created those dots on the graph, right? All right, so you'll have to do the same thing. So now in the homework, when it asks you to do that, you may create your dots in Desmos, but then pick the right answer picture from the My Math Lab screen. Does that make sense? Okay, all righty, so here, next one, let me make this lower so I can see it. All righty, so we just did everything that they just asked us to do. So we named those points, they're just reiterating what we just did. We just named each one of those points as we got to them. Domain and range, we haven't discussed yet, so let's see. All the X values are called my what? Domain. So whatever you input is always called your domain. Whatever you output is called your range. Okay, we're okay with this? Domain and input are the same thing. Domain and input are the same thing. Range and output are the same thing. So, if I asked you for this one and I said, what's the domain, you would say? 1, 2, 3, 4. If I said, what's the range, you would say? Done. 10, 20, 30, 40. So homework will ask you to do the same thing. When you're actually given the range and you see numbers in there twice, you don't have to repeat it. So if in this part, if I had this one and I said, what's the range? What you gonna say? Right here. Well, what's the domain? All the months, January, February, March, April, May, all the way to December. What's the range? There you go. You don't have to repeat 141, 141, 141, 141. It's just 141, 150, 160. That's the range. So in the homework, if they repeat them for the range, you don't have to repeat them. Alrighty, so here is the next one. This gives us a graph of this curve that you see on the right. We want to know, can we define what the domain is and what the range is? Now, what's the domain again? Most of the time it's going to be called the X values, or again, associated with the X axis. So what part of the graph are we looking? Horizontally. I just wanted you to tell me how wide this graph is. Where does it start over here? Where does it end? How wide is this graph horizontally? Somebody tell me. Look horizontally. How wide is the graph? From where to where? Notice that's what they put. They wrote it two different ways. So what you have here is a domain, and so let me say something about how they wrote this one. Can I cover this part of the board up, or you guys still writing what's on this board? No, okay. All right. So with that said, I'm going to say something about how they wrote the domain, because you're going to need to be able to write it the way they wrote it. They wrote the domain in two specific ways. They gave it to you in inequality notation and interval notation. So let me put that on the board. -3 less than or equal to x, which is less than or equal to 3. Or they gave it to you written in brackets forms. All right. Whenever you see, let me scoot this over here because I want to write something underneath it. Whenever you see two less than symbols with an X in the middle, this is called in between shorthand math. Right here. You say that as in between. You can say -3 less than or equal to x less than or equal to 3. That just says I want all the numbers what?
In between.
In between. That's what that means. When you see these two like this, it means in between. All the numbers in between what? -3 and 3. This is called what kind of notation? Inequality notation, because they have inequality symbols. The less than symbols are called inequality symbols. So this is shorthand. That's called inequality notation. So in the homework, if it asks you for the domain and it says write it in inequality notation, that's what it wants. This notation that you see here with the brackets, this is called interval notation. And it will usually use brackets or parentheses or both. When do you use brackets? If there are equal signs underneath both of those. You see equal signs? Brackets. Gotta have brackets. And then you only need the numbers, the start and the finish number. It also says that you have a dot on -3 and +3, wherever the graph, how wide the graph is and how tall the graph is. It's a closed dot. That means we included this dot here, and see the dot at the top? So that's where the equal signs come in. We included the -3 and the 3, so that's why they ended up putting equal signs here. So we got brackets. Could I have drawn that graph like this? So let me ask you a question. Here's the same graph. What did I change? What's the difference between that picture and my picture? Look what they did. What did they do?
Closed circle.
They put closed circles. What did I change?
You open circle.
I put open. Now, what does that change with these two notations if I put open circles? Do I get to include the -3 and the 3? No. So this is what it would look like if I change this one. It would go from -3, less than x, less than 3. What happened? What changed?
They don't have the thing.
Underneath the equal sign. I don't have the equal signs anymore. Why? Because these are open, so don't include -3 and 3. That says in between them, but don't include them. This one says in between them, but include them. Okay? How would I write it in interval notation for this one?
Are you parentheses?
Parentheses. And one last one I want to show you is, what if my graph looked like this?
So that means you got one line formula and the other one no line.
Correct. So here is -3, and that's gonna have an equal sign under it. This one won't. And then, of course, the interval notation. This one's gonna have a bracket. That one's gonna have a parentheses.
Excuse me,
Say it again.
can you tell me what happened? Interval, just start right at the interval.
Interval. The reason why I wrote this in interval form.
No, you changed it like, it's a parentheses.
Oh, how do I go from brackets to parentheses?
And that was like, why are you doing that?
Okay, so I want to show you, you can have it written multiple ways, but it depends on what the graph looks like and what it says. So if they've got dots on both ends, so your graph got closed dots on both ends, then it's going to have two equal signs here. Okay? And if it has two equal signs here or two closed dots, you're going to need brackets. So closed dots, you need brackets. Closed dots, you should have equal signs. Now, in this one, we had no closed. They're both open. I changed the graph that's on the screen and put both ends open. So if they're both open, you got to have parentheses. And we can't use brackets because they're not closed. So I got to use parentheses. So when both of these circles are open, you have to use parentheses. But in this one, I changed it and made one closed and one open. So the one that's closed gets a bracket. The one that's open gets a parentheses. The one that's closed gets an equal sign here. And the one that's open doesn't have an equal sign here. So equal sign, so this is called an equal sign underneath here. So no equal sign is the same thing as having it open. So open No equal signs equals a parentheses. Closed, gonna have an equal sign, it's gonna be a bracket. All right, so what we just looked at was which way? Horizontally, which was called the what again? Horizontally is what numbers? Domain. Okay, we want domain. We just did domain, which is all of our input values, which is the same thing as all of our x values. All right, that's all we looked at. They just asked you what's the domain, and we just described the domain in two different ways. We did what? What two ways did we show you how to do it? Inequality and interval notation. So now you know how to write it two different ways. All right, with that said, I want to now look at the range. What's the range? I want to look at the graph this way. We just looked at it, how wide is the graph. Now tell me where the top of the graph and the bottom of the graph is. Approximately where? Now you can see how they did it. They're closed dots, so we're going to have two equal signs. Where's the bottom of the graph approximately? Can you see it? It's not at negative 30, but it's somewhere in between 25, negative 25, negative 30. They called it. They said negative 27. So the bottom of the graph is at negative 27. Do we include it? Yes, because it's a closed dot. So notice you've got a parentheses with the negative 27. Y in the middle. Another less than symbol with the equal sign because it's a closed dot at the top. So look this way. How tall is that graph? Does it reach 40? Not quite. So they're saying we got all the way up to how much? 39. So this is what notation is this one again? Inequality notation. And what's this notation? Interval notation. All they did was put brackets. Why did we put brackets? Because they're closed. The dots are closed.
You said that was called an inequality notation?
Yes, the first one is. And the reason why I'm making sure I define this clearly, because in the homework it's going to ask you to write it in inequality notation, and then it might ask you to write it in interval notation. And you need to know how to do both. I sent them all to you. I sent everybody. If you don't have the PowerPoints, you need to send me an email back saying, I didn't get the PowerPoints. I sent it to you as a class. So just make sure you have those PowerPoints. All right, next slide. All right, for each of the following graphs, those functions find the domain and range. Now, there's a difference. What happened with this graph from the previous graph that we had?
They got the little 8, I forget what it's called.
The infinity symbol. Why do we need an infinity symbol?
Because it's like you can't tell where it stops.
It doesn't stop.
Right.
How do you know it doesn't stop? Because of the arrow, it doesn't stop. So did we have any infinity in the last graph we looked at? No. So do you need to know how to write this? Yes, you still got to know how to write it. So now let's look this way. Look horizontally. So if you're looking horizontally, and I'm going to do both inequality and I'm going to do the ones with the brackets and parentheses. So if I look to this direction, does it stop? No, it goes where? Tell me where it goes. To the left. When? How far? So how does forever? How do I write forever to the left? Okay, this symbol. Well, what else? What goes here with it? Gotta have a negative because it's going to negative infinity. Okay, so if it goes forever to the left, your negative infinity symbol should be over here. Comma. Now, does it go to forever on the right side of the graph? No, I need you just to look this way. X-axis, X-axis. What number does it start on the X-axis right over here on this side? 4. So here's a 4 here. Now, is that on 4? Does it touch 4 on the X-axis? That's considered closed. They didn't put an open circle there. So it's considered closed. So we're going to put a bracket or parentheses. Bracket. Alrighty? Now, when you write this in inequality form, this just says I want all the numbers less than or equal to 4. X is all the numbers less than or equal to 4. They both say the same thing. X is all the numbers less than or equal to 4. Isn't that what we wrote right here? Start at 4 and do everything that direction. That's what this one says. Here's my inequality version. Here's my interval notation version. All right, this was just my what?
Domain.
I just did the domains. What we got left to do? All right, so now which way do you want me to look?
Vertical.
I need to know this way, vertically. Where's the bottom of that graph, the blue part, where's the bottom of it at? Look this way. Don't look this way because you were tempted to go this way. Look this way. Where's the bottom of where does this graph, it's in between here, where does it start? Y'all looking like, you like, what way?
Six and -4.
All right, so let me do this right here.
Oh,
All right, I need you to look vertically along the y-axis. When we say vertically, where does it start? 0. So you're right. I just need to know, if you try to put that graph in between your hands, where's the bottom of this graph? It's 0. Look at the y-axis. Don't look at the x, because we ain't talking about x now. Look at the y. So for the y-axis, where do I start? 0. Right? So for the range, I'm starting at 0. Where do I go?
six.
Go up to 6. Does it stop? Does this graph ever stop? No. So can I say 6, 10, 8, 15, 55? Where does it stop?
Infinity.
So I should leave my hand right here, and this one goes on and on and on and on and on and on and on. So what goes on forever?
Infinity.
All righty. So it's going to go to infinity for that one. Because again, we're looking this way, so it starts here and just keeps going up and up and up and up and up. All righty, so I've got mine. This, do I put a parentheses or bracket on this side?
Parentheses.
Why?
Because it's infinity.
Infinity symbol always closes itself with a parentheses. All right, on this side, do I include this 0 or not? Is it touching at the 0 on the y? Is it touching the, yeah, it is. So I want a what? I want a bracket. All righty, so for the range, how do I write this? Yes.
When you say that it's not touching 0, what is touching 0?
What I mean is that
Or that it's touching?
is the graph on, when it comes to here, do we include 0 as part of the solution to this equation? So if I plug in, let me see if I'm saying this actually right. Because the graph starts right here, because this blue touches right here, we're saying it starts going up from right here. You see what I'm saying? I'm just saying, put your hand right here, and does it go up? How far up does it go? Starting right here. But I'm looking at this part, but I'm starting at that part from right here. Because if I can draw a straight line across right here, I'm saying the bottom of that blue starts right here.
So that arrow has nothing to do with this.
And not until we ask for the top part. The arrow starts, and now I know where it started at 0. Where does it finish?
2.
Right here, you're saying 2. What about the arrow?
That's the x though, yeah.
So you're saying, why? You're looking wide, I need you to look this way. Don't look this way. Don't try to say this way, because you look this way, then you're talking about x. I want to know how tall the graph is and how tall it's going to get. I know it starts at 0, but where does it end going this way?
Infinity.
The arrow says it's never going to stop. Here's what I'm asking you. If I had to graph this, again, I'm just making a, so here's what I'm saying. This is 4 over here, so I'm drawing this graph. There's an arrow right here. Does this arrow stop? No. So if I make it properly, this is going to keep going and keep going and keep going and keep going and keep going. So the question is this going to continue to get taller? Because of the arrow, it's going to continue to get taller and taller and taller and taller because of the arrow. So we only see a part that looks like it stops at 4. So when I do this and I say, where does it stop? This one never stops, but this part, it begins at 0. But we can only see the part that looks like it stops at 4 just because the arrow looks like it's at that part. But the arrow also means that it's never going to stop. So you only see a piece of where it stops. But it never does. Okay. Questions? All right, so that was me increasing the screen so we could see it better. All righty, so we've got our, oh, and the last part we didn't do, we didn't write it in inequality notation, has to use the variable for range. What's the variable for range? Because what we used for x was domain. What are we gonna use for the range value? What, the y value? Yeah, we're gonna use y. So y is gonna be all the numbers bigger than what? Is everything bigger than 0? Bigger than or equal to 0. So here, this says everything greater than 0 going to infinity. Questions? All right, this next one is, again, everything in here relates to real life, so we go back and pull it up, see how it relates. Usually what we're trying to see is there a relationship between the x and the y? Is there a relationship between the input and output? Is there a relationship between domain and range? So let's read it and see what the conversation is. For the following, determine whether or not the indicated relationship represents a function. Explain your reasoning, indicate the domain and the range of the function. All right. The PC industry celebrated its 35th anniversary in 2010. The U.S. sales of personal computers in the millions of dollars by year, which is represented by X, are shown in the table on the next slide. Is S a function of X? Remember I said they're not always going to use Y and X. They may use a different letter for something. So based upon the statement at the very end of this paragraph, what's the output and what are they representing output and what are they using to represent input? Which one is which? What's this one? This is S and this is X. One is input, one is output. Which one is which? S is output and X is input. Okay. All right, let's look at the table. All righty, so for each year, there's only one amount for the sales. Is this table S a function of X? Well, what did we say it had to be when we looked at all the what values? All the X values have to be different. Are they?
Yes.
Yes, they are. So is this a function?
Yes.
Yes, it is. What's your domain? The years. And what's your range? The sales. Now, this is in sales. That means they only sold 4 cents worth. Is that 0.04? They only had 4 cents worth of sales. The next one is 76 cents worth of sales. Does that make sense? No. What's wrong with why am I saying it that way and what's wrong with it? Go back to the previous slide. It says sales for the computers what? In the millions. Okay, so let's go back to the next slide. So that's 0.04 million. The next is 0.76 million. The next one is 6.6 million. The 1990 is 9.5 million. So these are millions, the sales in the millions. Okay. We okay? All righty. How can I write my domain in inequality notation? Based upon the chart that's on the board. I want you to tell me how to write my domain like this. Can I write it like this? Like this? Tell me how to write it. I want my domain in inequality. You already see the domain. Tell me how to write it. All right, I want all the numbers what? In between. And? Okay, tell me how to write that in inequality notation.
Should be 1975.
Less than equal to.
Okay?
Less than equal to 2015.
How do I write it in interval notation?
1975, 2015 in brackets.
Yeah, brackets.
Okay? This was my domain.
So if I want to be greater than,
Say it again.
if I want to be greater than,
What if you wanted which part to be greater than?
Signs.
Okay, so if you wanted to change these, you're saying change these and put them like this?
Yeah, they never
You can't
know.
do that. And it's never okay for you to do that. Whenever you have double inequality symbols, they always have to be less than. Never, 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 never will they be like greater. And if they do turn out to be greater than, you gotta turn it around and make them less than symbols. You cannot leave it like that. Whenever you have less than symbols like this, the smallest number should always be over here, and the biggest number should always be over there. But these better be less than symbols. So let me answer your question. What if it was written like this? And based upon what I just told you, what should you do if you have something like this? Turn it totally around. The symbols get flipped and the numbers get flipped because the smallest number should always be first. Yes.
You don't have to do nothing to flip it, you can just change it.
Just twirl it around. Twirl the whole thing around. If you ever see a problem that your answer's like this, twirl the whole thing around because these have to be less than symbols. Okay? All right, so that was what? The domain? What's the range? Somebody tell me how to write the range.
0.04 million.
Oh, I messed up now. 0.04 million?
Less than or equal to
Why?
No, why? Why? No.
What letters are they using? There we go. Okay,
Equal to.
I mean, it would.
done. How do I write it in interval notation?
Why?
Bracket 0.04 less than or equal to.
Comma.
No, comma.
Okay.
122.0 bracket.
Done. Okay. All right, questions? Y'all got this down packed, right?
Wait,
Yes.
interval, intervals, I'll put, yeah.
No. Interval, we can use interval notation for both input and output. This was range. We just did. So again, domain, again, we can use inequality or interval notation. Range, we can use inequality or interval
I
notation.
think range is on this, on the Y, range is Y.
Correct. But in this case, they called it S. But it is usually called Y, but
So
at
interval notation is always Y or range.
interval notation can be used for both. You see what I'm saying? I used, so here's my Y, which again, they're calling S. I use interval notation for the range. I also came over here and used interval notation for the domain. So you can use it for both. So I don't want you to think that you can only use it for the Y value. You can use it for both. Because you're just telling me what are all the X values, and this is the way to write. These are all of my X values. What are all the Y values? This is another way of writing, here are all my Y values. Okay? You want to know, you got two equations. Do the equations that you see define Y as a function of X? Yes or no? What would you have to do? Put them in the graphing tool. I want to know if they pass the vertical line test. So we go, put them in. 4x minus of y squared equals 4x minus 4. Go to decimals for me, please. So here, y squared, I'm just going to type it in. Y raised to the 2 power is equal to 4x minus 4. All right, you tell me. Does it pass the vertical line test?
No.
No. That's it. All right, what was the other one? Okay, negative x squared plus 6. Let's type that one in. Minus 6x, was that minus 6x? Backspace, let me see if I typed it right. Hold on. Plus 6x. Negative x squared plus 6x. All right, delete this one, because we don't need that one. All righty, here's my graph. What test am I doing? Does it pass? Okay.
Wait, not
What's yours look like?
Upside down.
And really thin.
It should be upside down.
Yours is up, mine's the opposite.
Yours opens this way.
Yeah.
Your negative sign. Did you put a negative sign right here? Look right here. Did you put a negative right there? Let me see it.
What's this egg?
Oh, that's because look at now again. Look at it's right. Yeah. Now, what's different? Now, when you ask me, say your graph doesn't look like mine. What's different on your graph than on mine? Look at mine clearly. What do I have? That's different.
Smaller.
No. Really look at it. Look like you're looking at it with a fine. What's different on your graph from my graph? Look at the actual, not the picture, not the curve. Look at the whole entire. Look at all the lines.
Mine's going to like 2,000.
Yes. So look and see where your x-axis and your y-axis. Mine are from over here. This is like from -5 to 15 is my x-axis scale. And my y-axis is from what's -5 to 8.
No, wait, I need to come back.
Let me see what you got.
I just got to zoom in.
Yeah, you gotta zoom to make sure you get it in there.
If you take it out, it look like that.
Yeah, look at your numbers. You got -1,600, -1,500. Yeah, that's fine. Now, or just go ahead and change it. So now, here's the point, guys. Yours doesn't have to look exactly like mine, but it should look pretty much like that. So meaning you can change, so I can change mine also. So watch what happens if I change mine. I'm gonna zoom like you did. Here is my zoom button. See what happens? I can't see anything. So you keep zooming. Now mine looks like that. It's still the same curve. What happens when you zoom, it changes your X and Y axis. It changes these numbers. So let me go click on the rich. Here's my rich. Guys, these numbers right here, this is my -59 is the farthest side to the right. Positive 70.355 is over here. That's how wide it is. You can change these numbers so you can have it what you want for your X and Y axis. So I can change this to be -5 to +5. And I can change my y-axis to be -5 to +5. And that's what my graph looks like. Now, if that doesn't give me the right picture, I gotta change my X and Y axis again because I can't see the whole picture anymore. So I gotta go fix it because it's not enough. So you go back to your, again, and say, well, let me play with this one and change this one to 20. But now I can't see the top of the curve. So I'm gonna change this one. So now, how do I know how large to make these numbers? Usually, I kind of get a gauge from what my equation looks like. If my equation has large numbers, I make them large. If my equation has small numbers, I make them small. So again, I look at my equations. I don't see any huge numbers in my equation, so I know I usually don't have to put huge numbers in. So there's my graph. Questions?
So it's like, if we were giving us something to be like, what's the equation for the graph?
If I give you an equation and I say, is it a function? Is y a function of x? You're going to go type that equation in here and see if it passes the vertical line test. This one pass? Yes, it does. All righty, back to PowerPoint. All right, so we're good with those. All right, it just said what we just said. That one, the first one passes, the second one doesn't. All righty, next topic. The next part of this wants us to make sure not only do we know interval notation and inequality notation, you need to know function notation. So this is what you need to know about that. And you may have seen it before. Just make sure you understand it when you see it. You see the F with the parentheses and an X in the middle and a closed parentheses? That's called function notation. So F, here's how you read it. F of X. That's read F of X. Now, the reason we use function notation is because the X happens to be, what is that, input or output? In most cases, X represents input. So when written in this form, I can tell you what number I want you to input. And then I'll give you the rest of the equation for you to input it into. So in this case, you have an equation. This is f of x is equal to, this is called the function. And they give you the rule. Let me make sure I'm writing this properly. They give you the rule. When they say rule, guys, when you hear me say rule, they give you what's happening inside the dryer. All right? This is what's happening inside the dryer. What are they doing? 2 times, raise it to a power of 3, add 5 times 2 to the, this is all that's happening inside the dryer. And it spits out a what? It spits out some dry clothes. You got an answer that's going to pop out from this. Okay? So here, if they put a number here for x, that's what goes into the equation. And once it's done, you're going to get an answer. So if I say, what's f of 4, what you going to plug into the dryer?
4.
Which is going to do what to it? All of this math that you see on this board, and then you're going to get an answer out. So everywhere there is an x, what do I put in the place of the x?
4.
A 4. So in your calculator, you should have a 4 here. Let me put this in black. 4 here, plus 5. And if you have your calculator, can you guys, somebody plug this in for me, please? Make sure I got it written right. Somebody tell me what I'm doing.
All that math.
All right, y'all check my math now. Did somebody already get the answer on the calculator? Now, all I did was break it down and actually do it by hand. That's not required. That is not required on, what is that? 208.
45.
Say it again.
45. Yes.
You got 45?
Yes. Okay, never mind.
Okay, so I'm just trying to make sure it looks good.
Yeah.
That's 127.
Negative 127?
No, no. I'm just doing it by hand so you can see that you come up with the same answer. All right, so my final answer, y'all said is what?
81.
All of that is up there, 81. So, f of 4 equals how much?
81.
And when they ask you to write your answer in function notation, this is what they want. If they say write your answer in function notation, they want you to write it just like that.
And this is, and the name of these problems are called solving equations.
This in particular is you're evaluating. When it'll say evaluate f of 4, that means plug in 4. Solving, we'll get to a different part where it'll actually say solve. This one should say evaluate because they give you a number to plug in.
Will you say the box called?
Hmm?
What the box called?
Oh, this right here is function. They'll say write your answer in function notation. So this is what they want when they say write your final answer in function notation. They want the answer written just like that. Okay, questions?
Are you allowed to use calculator on the time?
Absolutely.
Anyone?
Preferably you get the ones that, if you already have a calculator, that's fine. My preference is that you get a calculator where you can actually see what you type on the screen. Now, sometimes you'll type something and you hit equal and it disappears and just gives you the answer. I would like for you, usually you can get a $20 calculator, it's the TI-30 something, but it actually lets you see what you type on the screen. So if you do make a mistake, you don't have to wonder, wait, what was my mistake? Did I put a minus sign in the wrong place? So that's the preferred. And like I said, don't buy the $100 calculator. $20 will suffice for a calculator. And you want a calculator that has not just add, subtract, multiply, and divide. That's the $5 calculator. Don't get the $5 calculator. No, get the one, if it's got this button on it, it'll say log, L-O-G, square root button on it. It's got raise it to a power button, X raised to the something power. If you've got these buttons, you're good. It has to have the log button. So if you don't have the LOG button, it ain't the right calculator. Because we'll get to that towards the end of the semester. It still shouldn't cost you over $20. Okay, question. All right, so we plugged in a 4. What does it want us to go back and do the second part? Plug in f of -2. And we do the exact same thing and we're going to get the answer 45. Question? And in most cases, like you were asking me, the question is going to say solve. A lot of times it's going to say evaluate, or in this case, notice what it says. Use the equation to find, it'll say find f of -2 or find f of 4. All right, next slide. Here's where they did all the work for both. Next slide. Alrighty. Back to real life again. All right, the points on the graph give the number of elderly men in the workforce in the millions as a function of G, as a function G of the year T for selected years. What letters of the alphabet are they using for the variables this time? G and T. Now you got to know which one is output and which one is input. Which one do you think is output and which one is input? G is output and T is the input. Now, what do the G and T refer to? Whenever you read these problems, we want to make sure we understand what G and T refer to. Notice it says the year T for selected years from 1950 to 2050. Again, T in most of this class, T will always be time in seconds, minutes, hours, years, days, always. T will usually represent some sort of time. Time will always be input. Time will always be input. That means the other variable is the output. So, what's the conversation? These points on the graph give the number of elderly men in the workforce as a function G. Okay? They use the number of elderly men as G. And this is the number of men in the millions. So, here we go. In 1950, how many elderly men were in the workforce? 45.8. Okay? 45.8? 45, just 45 men? 0.8 million. Just make sure you understand this is 45.8 million men, not just 45 men. All right, in 1960, how many elderly men were in the workforce? 33.1 million. In 1970? Okay, something happened. What happened in here? There's a dip. In 1980? 1980, there's a dip. What happened?
They died.
Oh, okay. So did something else happen that it dropped? It dropped down to 16.4 million. The retirement could have happened. Yeah, absolutely. All righty. So now if we look at close to where we are now, it's picking back up again. Look at where we are in 2020. This is an estimation of this is called a prediction. We use the information that we currently have to make a prediction about the future. So based upon what's happened in the past, they're predicting by 2020 there will be 21 million elderly men in the workforce. Why they having to go back to work? Okay, so again, we don't know. So again, just look at that as if there's an X, is there a corresponding Y value that's going with each one of those values? What's the X? What's the domain in this case? The year, so 1950, 1960, 1970, 1980. All these are my domain. What's my Y values? Or in this particular case, they call it G. Again, what is this number again? These numbers that's on these dots. The number of elderly men still in the workforce. In the millions. So what's my range? You gonna tell me again what's my range? 45.8. Yeah, million, 33.1 million, 26.8 million, 19. So you see what I'm saying? So when we ask you for the range, how would I write that range?
You can ignore everything but the lowest one, right?
You can do, say it again.
You can ignore everything but the highest and lowest ones, right?
Well, if I want range, I want you to look this way. Range, where's the range? It's gotta fit in between. Where's the bottom of that curve? Where's the top of it?
0.
Well, wait, let me see now. Okay, so did it drop down to 0 men in the workforce? Okay, did it drop down to 10 million men in the workforce? All right, what's the lowest point you see in terms of number of men in the workforce? Okay, so 16.4 is the bottom. What's the highest number for men and elderly men in the workforce? You got it? That's your range. From 16.4 to 45.8. We're good? That's your range. So if I ask you for the range, that's what you would give me. If they want specific points, you would give me the specific points. All right, question. All righty, the question says find and interpret 2020. G of 2020, what do I do? You tell me. If it says find and interpret 2020, tell me in English, what does G of 2020 mean?
21 million.
Say it in English. Give me a sentence.
Do the math.
So we gotta put it in interval notation?
No, they just want you to, when it says interpret, they want you to explain to me in English. If you had to tell your mama, your daddy, your auntie, uncle, what that means, what does G of 2020 mean? Now that you're looking at the graph, give me a verbal English statement of what you think that means in plain English. Thank you. In 2020, there were approximately 21 million elderly men in the workforce. Done. Those will be the verbiage that you would see in the homework. It would pick A, B, C, or D, and you'd have to pick the one that states it the best. You make sense? Okay, all righty. So with that said, all right, next slide. We're okay? All right, there it is. So in 2020, there were 21 million men in the workforce. They just stated it here. Same sentence we just said. There it is. All right, let's see if there's anything in this slide. The points on the graph give the number of okay, blah, blah, blah. Okay, now it's going backwards. Now this time it's asking you, what year was it that the output was 19.6 million elderly men? Now it's asking you to look at the Y and look at the number of millions of elderly men. What year was that?
2011.
So I want to know, was it 19.6? So where is 19.6 on the graph?
2030.
So somewhere in, let me see if my cursor was,
Oh, okay, I'm looking at 2010, okay.
so now, where or what year were there 19.6 million men in the workforce?
2030.
So, and again, there's right here.
Okay, look, she did the same thing, she went 2010.
Yeah, I immediately went over here because I saw this 19 over here and I started to go here and then I saw it was right here. Question. So now we're going to do 2030. 2030, so G of 2030 equals, so in 2030, there were 19.6 million men in the workforce, elderly men. Question? All right, let me put it back. All right, page down to the next one. All righty. Let's see what this one wants us to do. Okay, what can we say about the elderly men from 2020 to 2040?
It go down.
It goes down. It looks like it's decreasing. Maybe it means all the grandchildren are taking up the slack so the elderly men don't have to work. Say it again. Okay, all right, so that's all they want you to see is that, can you tell from the graph that it's decreasing? And that's it for that one. Next one. All right, let's see, same slide or same graph. What is the maximum number of elderly men in the workforce during what? During the period shown on the graph?
During 1950, it was 45.8.
Yeah, I mean, when we first looked at this graph, 1950 was the highest number of elderly men in the workforce, which is 45.8 million. All righty. All right, I think I got last type of real world problem. All right, real world word problem. All right, public healthcare expenditures. Do you know what that is? Public healthcare expenditures. What is that? How much money? Yeah, how much money you spend on healthcare? Okay, so for those of us who actually, if you're working or if your parents are working and you're still on their insurance, they're paying something for healthcare. So again, or it could be public health, that people that don't have medical coverage through their company and they're on public health care as opposed to us paying for our premium that we pay in our paycheck. All right, so public health care expenditures from 1990 to 2012 can be modeled. And again, it says that is accurately approximated by the function given. All right, so they're giving you an equation modeling the expenditures for public health care. What's the equation? E of T is equal to 738.1 times 1.065 raised to the T power. So now I need to know where E of T is in the billions of dollars and T is the number of years after 1990. So my question is to you, what variables are they letting represent the input and the output? What's input in this case? T. T is input. Years will always be input. What's the output?
Billions.
And in billions, what variable are they using for it again? I heard it. E. E is for expenditures. That's just how much money we're spending on public health care. All right. So what value of T represents 2010? So let me make sure you understand the question. T is the number of years after 1990. So what's the T value for 2010? T is the number of years after 1990. So how many years is 2010 after 1990? 20 years. How do you get 20? How do we get 20? 2010 minus 1990. You just subtract, literally. So in your homework, it's going to give you quite a few questions, especially as you go through this class. It'll say T is the number of years after 1925, or X is the number of years after 1955. Every time it tells you that, you have to subtract to figure out what T is. Yes?
On the homework, does it tell you like when you got it wrong and stuff like that?
Yeah, it'll mark it wrong. It's going to mark it wrong if it's wrong.
Okay.
It will mark it wrong. It'll say this, I mean, literally, it's just going to say wrong. It'll put an X on it. But here is, I'm just trying to make sure, because the number that you plug in won't be the year. You're going to plug in how many years after 1990 that is. So to use that equation, I want to find out how much money did we spend on public health care when? In 2010. What number do I plug in for T? You can't plug in 2010. What you going to plug in? 20. T is the number of years after 1990. So you plug 20 into the equation. So somebody tell me. So you're going to have E of what? E of 20 equals, somebody put that in the calculator. 7 what? 38.1 times 1.065 All right, raised to the 20th power. Somebody tell me what that is on the calculator. And let's look at the next slide. All right, you may not have finished on your calculator yet, but this is what you get. $2,600.80 billion is what we spent on public health care in 2010. Does that sound about right? I mean, just think about it. We all paying for health care some way or somehow. But this is just what we spent on health care in 2010. Do you think that number has increased? Yeah. Did we stop having babies? No. We have not. Even though I know people are passing, but we still ain't stopped having no baby. Okay, so again, if you put this in your calculator, you should get $2,600.8 billion. Question? Alrighty, this next part says use the same model to estimate the expenditure for healthcare in 2015. Do I plug in 2015? No, what should I do? After what? After 1990? How do I do that? Subtract what? What two numbers do I subtract? 2015 and 1990. How many years is that? 25 years. So plug in 25 into the equation and tell me what answer you get for how much money we spent on healthcare in 2015. Did y'all get the answer we got? Did y'all get something different? Well, let me show you the web calculator that I usually use in class when we're here, so that if I need to actually calculate, you won't be allowed to use it on a test, but I will show you where it is. All right, web 2.0 calc.com is an online, you don't have to download it or anything, okay? Just type in the equation. What do we have? What was that? 738.1 times 1.065. Whoops, missed my time sign. Is that the right thing, y'all? Raised to the 20th power? 25 power. Thank you. Thank you, thank you. 25 power. It equals, there we go. All righty. So this is what we got, $3,563 billion in healthcare. Is that what we got when we look back at this PowerPoint? Let me look. Yep. We got the same thing. All right, questions? Okay, so since we went over the syllabus, and let me stop this since I don't need any more of it.